Okay. Hello everybody. Welcome to the eighth lecture of differential privacy. And today we're gonna finish the basic DP section. And by giving the last lecture about the privacy accounting before we move on to talk about differentially private machine learning. So today, yeah, a lot of the materials that we covered last time will be put into action so that we can create algorithms that helps us to do tight privacy accounting. Okay, as a quick recap of the last lecture, so the primary focus of the last lecture is to introduce two equivalent definitions of epsilon delta differential privacy. So we can redefine DP via the hockey stick divergence, an upper bound of the hockey stick divergence that applies to all pairs of neighboring data set, or alternatively, we can define differential privacy according to the kind of a lower bound or a performance limit of the adversary's ability to recover which data set is it that gives rise to the output of the randomized mechanism. Right, it turns out that these descriptions or characterizations, they are if and only if to suppose the mechanism satisfy epsilon delta dp. And using the hockey stick divergence characterization, we derived what we call the analytic Gaussian mechanism, which precisely describes the epsilon delta trade-off for every epsilon delta at the same time. And this is one example of so-called mechanism-specific analysis, which we'll spend more effort in today's lecture. Okay, to give a bit more details, the hockey stick divergence is one particular f divergence when the f function is taken to be the rectifier function, or 0 on the left and then linear at this alpha parameter. Like something like that. So it measures the discrepancy between two probability distributions. It turns out that it is equivalent to epsilon delta dp. And when we just write out the definition of the hockey stick divergence, we can rewrite it in terms of the privacy loss random variable of some p and q. Let's say that p is m of d and q is m of d prime. This inequality is identical to this other inequality that's written in terms of the cumulative distribution function of the privacy loss random variable LPQ and LQP. And if this holds for all neighboring data set D and D prime, then we equivalently defines that this mechanism M satisfies epsilon delta dp. Like using this, we can get like the optimal Gaussian mechanism that we've seen in the last lecture. The other equivalent definition for differential privacy is a so-called trade-off function based definition. So a trade-off function is a trade-off between the type 1 error and type 2 error that an adversary or an attacker, when trying to make an inference about whether any individual is in the data set or not. And the trade-off function says that the type 1 error and type 2 error cannot be small at the same time, or in other words, like this region is impossible for the adversary to achieve. So this provides an intuitive explanation of the guarantee of differential privacy on how it prevents the adversary from being successful in identifying individuals. And anything above this line is possible for any epsilon delta dp mechanism. So this piecewise linear function has four legs. So first of all, like this is a region where there's a small probability delta happens. So this is a region where we simply give up on privacy, and similar to this region. And this line is described by described by this linear function. So beta is equal to 1 minus delta minus e to the power of epsilon alpha. So the slope here is minus e to the power of epsilon, and the intercept here with the vertical axis is 1 minus delta, right? So by flipping this to the other side, by taking the inverse of it, and then take the pointwise maximum of these two, like this is the other leg. So this corresponds to this line. Then we get epsilon delta dp, and this trade-off function. Yeah, it's just a very interesting way of looking at the same problem from its dual. And after introducing these two hammers and these two equivalent definition of epsilon delta differential privacy, then we went on to talk about the following argument. So for any given mechanism, let's say that this is a Gaussian mechanism that add noise to f of some query with low sensitivity. Like we can describe this mechanism by saying that it satisfies epsilon delta dp for some parameter epsilon and delta, but yeah, just describing this mechanism with just two numerical numbers, epsilon delta, turns out to be somewhat crude, and this is a lossy way of representing this mechanism. It also satisfies, say, many other privacy properties that are not captured by just epsilon delta dp with a fixed pair of parameters epsilon and delta. So what we can do is to think of more fine-grained description of the mechanism using using a function, and these functions provide more details on the behavior of this mechanism when it is under attack, when some adversary is trying to make inference about you as whether you are part of the data set or not. So a couple of examples of these are things that we've covered, and it's just now they become functions. Say the privacy profile is defined to be the function of delta for any chosen epsilon parameter. A privacy profile, say the Gaussian mechanism, not just satisfy epsilon delta dp for one single delta and epsilon, but it also satisfy epsilon delta dp for other pairs of epsilon and delta, and this captures them all. So the privacy profile of a mechanism M is defined to be defined to be the pointwise maximum of its hockey stick divergence for all pair of neighboring datasets. Similarly, like the trade-off function, the trade-off function can be more fine-grained than the one that I've shown you earlier, which is equivalent to epsilon delta dp. For each mechanism, there is actually a better trade-off function that we know, like suppose this mechanism also satisfies epsilon delta dp, that it operates well above these regions that's carved out by this piecewise linear curve. On the other hand, for each mechanism, like where exactly it is, so it really needs to be written down carefully in order to figure out what exactly this trade-off function is for M. And we learned the Renyi divergence as an upper bound of the Renyi divergence of order alpha, and we call this alpha epsilon Renyi differential privacy. But alternatively, we can also think about this as a function. So Renyi dp describes a mechanism by a function of the entire family of Renyi divergence for all alpha larger than 0. And this is just a pointwise upper bound of the alpha order Renyi divergence over all neighboring datasets X and X prime. Right. So these are the three major ones. There are others, like we talked about the privacy loss random variable. For each X and X prime, there is a privacy loss random variable that we know has a lot to do with the privacy guarantee that we end up getting in the end. We'll see how everything above is related to the privacy loss random variable and how to deal with this maximization, because it's not intuitive at all. Like, how do we simultaneously handle a possibly infinite number of privacy loss random variables in this case? So there might be situations where the data space is discrete and small. Say in the randomized response, we know that the data space is just either 0 or 1, and there's only one pair of neighboring data sets. So in that case, the privacy loss random variable approach, or the so-called privacy loss distribution formalism, can be used naively. But in more general situations, when the space of the data set is more complex, then doing this maximization will be non-trivial. So we'll talk about that in the later part of today's lecture. So let me provide like more a bit more intuition about this connection between the trade-off function and the privacy profile as two like in some sense equivalent functional description of this mechanism M, and they are related to each other through they are related to each other through convex duality, or the Finchel conjugate. So this is a theorem from Jinshuo Dong et al. Which says that the privacy profile of any mechanism is equal to 1 plus f star. So this star means taking Finchel conjugate when the input is e to the power of epsilon. So it might be a bit difficult to understand from this direction, but maybe now let's see how we can go from the dual to the primal by thinking about how we can represent this f using the family of all epsilon delta dp's, right? So from this figure, it is pretty clear. The red line is what the Gaussian mechanism with sensitivity 1 and noise level also 1 satisfies. So don't at all define this to be the Gaussian differential privacy. But this red line is the trade-off function that's specific to Gaussian mechanism, and it completely characterizes a Gaussian mechanism. But an alternative way of thinking about this trade-off function is to look at the local linearization of it, and to look at the pointwise linear lower bound of this function. And if we enumerate all possible linear functions that support this trade-off function from below, and then that provides an alternative description of this line in red. Okay, how do we say that in words? So clearly from the last lecture and from our understanding of epsilon delta differential privacy, we know that all of the epsilon delta differential privacy would imply that the trade-off function satisfy beta is larger than 1 minus delta plus alpha to multiply with e to the power of minus e to the power of epsilon. So this is a slope, and this is an intercept. And what this is saying is that for, like, suppose I'm saying that Gaussian mechanism satisfy one particular pair of epsilon delta dp, it means that this line is a lower bound of this. This line is a lower bound of its trade-off function, and this is 1 minus delta, and this is the slope is minus e to the power of epsilon, and it overlaps with this GDP at one particular point, right? And as we adjust this epsilon and delta, then we get like other lower bounds. So and then like from a known delta epsilon, so this is a trade-off function of this mechanism, we know that beta is larger than max of all possible epsilon plus alpha minus e to the power of epsilon. Right? So we know that the trade-off function satisfy this form. Right? And what is this? And max of epsilon can be rewritten as max of e to the power of epsilon. So it will be alpha. So let me use, since these are scalars, but let me use a slightly more general notation so that you it is more familiar to you. E to the power of epsilon plus 1 minus delta m epsilon. Okay. So this is a function of epsilon, and this is a linear function of yeah, you can also rewrite this as delta tilde and reparameterize it with a e to the power of epsilon. Okay, you can rewrite this. And for those who are familiar with convex analysis, yeah, then you can move this +1 out, take this one out, and this checks the definition of convex conjugate, right? So you are getting the pointwise maximum of this particular function with an additional linearization term. So this this is the convex conjugate of I guess let me also add minus e to the power epsilon here, minus e to the power of epsilon, and this means conjugate. Yeah, I like the input is taken to be this alpha as input, right? So what this says is intuitively is that where I'm enumerating all possible epsilon delta dp properties of this mechanism, and then want to find this pointwise lower bound for this trade-off function, and then by convex duality, these two representations are equivalent, and we're able to just by cutting it at every possible location, I'm gonna be able to carve out this very smooth curve that's out there. Okay, so this half only gives you up to this point in the middle, because once e to the power of epsilon becomes smaller than 1, like this is the slope being -1, then it doesn't give you anything anymore. What you need to do is to just flip it to the other side and use the other half of the linear supporting lower bound that's coming from epsilon delta dp, and then repeat the whole process. Then you will be able to carve out the other half of this Gaussian mechanism. Okay, so it's like heavier than necessary machinery to use the convex conjugate to do this, but that's precisely what these are. It's simple in 1D. So you can more easily understood it by this idea of supporting a hyperplane or supporting linear functions on this trade-off curve. All right, yeah, I hope that sheds a light on the connection between the trade-off function and the privacy profile. In today's lecture, we're going to talk about how we can do mechanism-specific composition. And introduce two algorithmic ideas called the RenEDP content and Fourier content. We will also talk about how do we do a unified treatment of these mechanism-specific analysis using something called dominating pairs and dominating privacy loss random variable and its characteristic function. And I'll explain what are the benefits of representing the mechanism in this fashion. And lastly, I hope I'm going to be able to give you a demo on how to use autodp to represent DP mechanism and compute privacy losses and calibrate these mechanisms parameters to achieve some predefined epsilon delta. Yeah, it will be quite useful for your project if yours is a more practical project that implements these noise adding mechanisms and evaluating the privacy utility trade-off, and then the autodp is something that you might need to use. Right. So the reading materials for today's lecture are this paper that Yu-Xiang and Jinshu and myself wrote this year, and also the tutorial of autodp that's on the on the project website. All right, let's talk about the composition of mechanisms. We briefly talked about this last time. So the idea is that like the mechanism-specific analysis, like characterizing the trade-off function or the privacy profiles, we can only do that for simple mechanisms because it involves like detailed mathematical computation and derivation and so on, and you know, PhD students are expensive. we cannot afford to do this at a large scale when people come up with new mechanisms every day. But the nice thing about differential privacy is that everything by design is quite modular. We have basic building blocks of the mechanisms, and we can compose them together into more complex mechanisms. We can use pre-processing and post-processing to manipulate them so that we create a new mechanism. So the composition is a key algorithmic designing tool that we use, and we've seen that with appropriate basic mechanism and compositions, we can create mechanisms such as private multiplicative weight update that achieve something that's quite remarkable. So, but suppose we have this functional representation for individual mechanisms that we compose. The question is that what is like a similar function representation for the composed version of the mechanism? So more specifically, let's say that we have the RenEDP of epsilon m1 to mk. What is the RenEDP as a function of m1 to composition with everything in this list? And similarly, suppose we have the privacy profiles for m1 and privacy profile of mk. So what is a privacy profile of m1 to mk after they are composed? Right. So I'm not distinguishing like adaptive composition or non-adaptive composition, because everything that we're going to be saying simultaneously also applies to adaptive compositions through the kind of martingale type argument. So that will be clear later. So I'll mostly wave my hand and then not worry about the dependence on the output of the previous mechanism. So technically speaking, this mk is a function of the output of all previous mechanisms and also the data set. Yeah, but for now, let's just consider that mk is takes the data set and it is chosen, say, maybe already ahead of time. For RenE differential privacy, the answer is quite straightforward. The answer is that you simply add them up. To say it differently, so epsilon of m1 to mk is equal to or at least smaller to the sum of epsilon mi from 1 to k. Yeah, so this is due to the nice property of moment generating function and the fact that how our RDP is defined. So take the definition of the RenE divergence, which gives us the e to the power of alpha minus. This is Q alpha and log P over Q, right? So then suppose we have another mechanism that got added up to this. This is Q prime, P prime, and Q prime. And then we can simply get this to be the log of E, the product of expectation, and because these two are independent, or if it is a martingale, and then it also factorizes, then this becomes a Q, like the joint distribution and Q prime, and then in the product you get E of alpha and log of P prime Q prime plus log of P prime Q prime, and this becomes alpha minus 1 log of E Q cross with Q prime and E of alpha log of P prime, and this is by the property of log Q times Q prime, which by definition is a alpha's order RenE divergence of P cross P prime and Q cross Q prime. right? So this is saying that for every pair of neighboring data set, the Renyi divergence simply adds up, right? And if we have RDP that is an upper bound for this one and for this one and that one separately, this is smaller than epsilon m1 alpha, and this is smaller than epsilon m2 epsilon alpha m2 alpha, and then the composed the composed mechanism is so this is basically upper bounded by just epsilon m1 alpha plus epsilon m2 alpha. Yeah, so the issue of this approach is as we've seen last time, is not really tight when we are trying to convert it back to the epsilon delta dp. So we can use a tail bound of some from the Chernoff's argument and get a like this is also moment generating function. Therefore, we can use a Chernoff argument to optimize over alpha and then get a tightest upper bound that can be obtained using the Chernoff's method. But as we've seen from the analytic Gaussian mechanism, it's not really tight. For the other two functional representation, the trade-off function and the privacy profile, they are somewhat more complicated. And yeah, we'll explain that in the subsequent slide. But the nice thing about the Renyi DP is that it allows us to very easily implement this in practice. So provided that we know the Renyi differential privacy of individual mechanisms, we can pass that into something called a Renyi DP accountant, or also known as a moments accountant. And by simply adding up their log moments or adding up their Renyi DP upper bound, and what makes things better is that we don't need to know like what is the right alpha parameter to choose ahead of time. We can just use symbolic functions like lambda functions represented in Python to just represent that as a Python function that takes an input alpha and then simply add those symbolic functions together. And only at the very end, when we want to convert it back to epsilon delta dp, you can choose your favorite delta, and then the data structure will output this epsilon by doing the RDP to DP conversion in the end. Yeah, so this has been the workhorse in a lot of the recent differential privacy applications. For instance, those that involve like noisy stochastic gradient descent for differentially private deep learning. Yeah, from this paper. Yeah, and this is an RDP paper, and this is a paper that proposes this analytical moments accountant. Yeah, like I said, the conversion from Renyi DP to epsilon delta DP is not really tight. And I wanted to use these three figures to very explicitly illustrate what's really going on. So like it has a lot to do with how Renyi DP is defined and how it affects the individual mechanisms in ways that are different. So I'm comparing the Gaussian mechanism and the randomized response mechanism. As we know that the randomized response mechanism is a pure DP mechanism, and then it also satisfy the concentrated DP. Okay, and when it satisfies the concentrated DP, then it means that in terms of the Renyi DP, it is dominated by the Renyi DP of a Gaussian mechanism. So both the RR and GM, so when their parameters are chosen carefully, they satisfy like one ZCDP, one concentrated differential privacy, or this linear line is a exact Renyi DP of Gaussian mechanism. So whatever RDP conversion that converts the RDP to the epsilon delta DP must simultaneously apply to both mechanisms. Do you guys follow that? So since this blue line is upper bound of the dashed red line, therefore, like if we want to convert the Renyi differential privacy into epsilon delta differential privacy, then that conversion should return epsilon and delta that simultaneously, say we fix delta and want to get epsilon. So the conversion should return something that simultaneously apply to Gaussian mechanism and randomized response. Okay, so the optimal conversions that one can work out. So it takes some heavy mathematics to do that by first converting to trade-off function and then trying to use the differential conjugate and then construct the corresponding epsilon delta dp. But by doing that, like you can work out the optimal RDP conversion is this blue line on the second and third figure. So the second and third figure, they're equivalent. They are just they're dual to each other. So the second figure, we are plotting the trade-off function representation, and for the third figure, we're just directly plotting the privacy profile, but inversed. So the horizontal axis is delta, the vertical axis is epsilon. So what we can see is that the epsilon delta dp from Gaussian mechanism actually intersects with the epsilon delta dp of the randomized responses, which says that let's look at the third figure. For instance, at this point, we know that this is a property that Gaussian mechanism satisfies. It is say 0.75 and 0.4, 0.35 dp. On the other hand, the randomized response doesn't actually satisfy this because the optimal privacy profile for randomized response requires a larger epsilon at the same delta. So in some sense, so even though the Gaussian randomized response dominates Gaussian mechanism or is more private than Gaussian mechanism for all parameters in RenEDP, it's like there isn't the same partial order that can be defined like for these mechanism with same parameter in epsilon delta dp, and the kind of best conversion that you can hope for from RDP to DP must be above. Wait, what's the? Okay, yeah, must be above. Must be also above this line of randomized response. Okay, so this slide demonstrates that RenE differential privacy and approximate differential privacy, they are completely different objects, and they may not have the same pointwise maximum, and those pair of neighboring data sets that attains these upper bounds might not be the same pair of neighboring data sets. Even though both of them are natural. All right, sorry guys for the technical glitch. I had to, what happened was that my laptop died and I had to stop the lecture over there and then record the second half of the lecture asynchronously and then share with you guys this video. Yeah, sorry for those who come to the lecture in person, and I apologize also to those who were on Zoom and had no clue what was going on. Yeah, I hope Xuandong was able to send that note on Piazza, so now you guys all know what's going on. Okay, so let me continue with the lecture and then recall that we've been talking about the composition of mechanism-specific approaches, and then we finished talking about the composition of RenE differential privacy. For the composition of the trade-off function, it's somewhat complicated, which involve the convolutions of the mechanisms with this tensor product signs. And what this actually means is that if there exists some P and Q such that F is if there exists some P and Q such that F is equal to the trade-off function of P and Q, and G is equal to the trade-off function of P prime and Q prime, then we can define this F composed with G in this way. So it basically involves us to finding what P and Q are and P prime and Q primes are, and then basically by doing the convolution of the probability density function of this P and Qs separately, and then that creates a trade-off function for this F composed with G. The operations could be somewhat complicated and numerically unstable if this P and PQ and P prime Q prime are chosen appropriate are not chosen appropriately. On the other hand, like it is also known that the choice of PQ and P prime Q prime are not unique. So the approach proposed by Dong et al. Is to appeal to the asymptotics. So specifically, when we are composing an arbitrary sequence of mechanisms and each one of them satisfy F differential privacy with some regularity conditions on these individual Fs, then there's this universality result that says that it doesn't matter what this individual F look like. The composed mechanism will satisfy an F differential privacy that looks very much like that of a Gaussian, that of a single Gaussian mechanism. So this is illustrated that in this figure. So when the red line is an exact composition by using this rule of 10 randomized responses and 10 pure DP mechanisms. And what we can see is that even with just 10 compositions, what we end up getting is still a piecewise linear line, but it looks already very similar to the continuous line that are coming from the asymptotic distribution of a Gaussian differential privacy mechanism. Yeah, so what I want to highlight is that this central limit theorem, while it is very interesting on its own right, and it talks about something fundamental about the trade-off function, if we want to apply this central limit theorem to obtain epsilon delta dp, you will see that you cannot actually make delta very small. Specifically, like the central limit theorem shows that the trade-off function converges, say, in L infinity, but towards the two ends of this trade-off function, like even a tiny bit of differences in the trade-off function will result in hugely different epsilon deltas that you end up getting so there are actually high order differences between the distribution you converge to and the actual distribution that you get. And it doesn't matter for the central limit theorem to hold, but it does matter if we want to show epsilon delta dp with extremely small delta. This is an important consideration, and it's also partially the reason why the central limit theorem approach doesn't actually solve the entire problem. Yeah. But by the way, the fact that there is a central limit theorem should be quite intuitive, because we've seen that the composition can be thought of as a summation of summation of almost independent random variables, and we know that the summation of independent random variables converge to a Gaussian distribution in distribution. So this is the same effect here, and the idea was formalized to show that the composition of arbitrary sequence of mechanisms satisfying some weak conditions converges to that of a Gaussian mechanism. All right, the composition of the privacy profiles is also somewhat tricky. So in principle, one can enumerate over all neighboring pair of data sets and then compose this sequence of mechanism by working out the privacy loss random variables for each one of them and work out a tail bound for each neighboring pair. but that's not very computationally efficient since there are possibly infinite number of neighboring pair of data sets in the data space. And practical implementation of this approach requires us to know the worst pair of data sets to make it efficient. And as a matter of fact, this worst pair of data set might not be the same for different choices of epsilon in the privacy profile. So it's still somewhat difficult to do this in practice. And the thing is that even if we know what the worst case pair data set is for individual mechanisms, and it is not easy for us to construct the worst case pair data sets for the composed mechanism because the worst case pair data sets might be different. And the individual worst case pair data set for individual mechanism M1 to MK might also be different depending on which mechanism it is. Yeah, for this reason, we are hoping to get something that's slightly more general, that allows us to consider the worst case pair of the worst case pair for individual mechanism and somehow extend that to the composition. That brings us to the idea of dominating pair distributions. And the dominating pair distributions is defined using the hockey stick divergence. So it basically says that so for any neighboring pair, and there exists a P and Q, and this P and Q, notice that they are not necessarily coming from any neighboring pair of data set. They are just the two generic pair of distributions. Like the simpler they are, the better. And suppose this single pair of distributions can be used to provide an upper bound of the privacy profile of mechanism M. Then we say that P and Q is a dominating pair for M. When this inequality is true with equal sign for all alpha, for all parameter alpha of this hockey stick divergence, then we say that PQ pair, this P ordered PQ pair, is a tight dominating pair. So we've shown that very interestingly, for every mechanism, a tight dominating pair exists. So this is non-trivial. So clearly a dominating pair exists. So this is a trivial statement because we can simply choose a P and Q to have different support. And then the right hand side is always unbounded, and so that is a dominating pair, but a trivial dominating pair. What theorem 1 says is that there always exists a single pair of PQ such that the equal sign is taken for the entire domain of alpha. Okay, I won't be able to tell you how this is proven, but the existence of this PQ pair is already giving us hope that we can do something more general with by composing the privacy profile. The second statement that we know about dominating pairs is that they compose adaptively. So the idea is the following: suppose you have M1 and M2, and M1 is dominated by PQ, and M2 is dominated by P prime, Q prime. Then this implies that M1, M2 together, the composition of M1 and M2 is dominated by P, the joint distribution of P prime and the joint distribution of Q prime. Yeah, this will turn out to be very useful as we derive the general composition theorem for privacy profiles. And this shouldn't be too mysterious to you, since we have seen that there's a connection between the privacy profile and the trade-off function representation of this mechanism M. So it can be shown that if PQ dominates M, if and only if the trade-off function that we can write down based on this PQ also satisfies is a valid lower bound for the trade-off function of M. To say it differently, so if PQ dominates M, then the corresponding trade-off function that we can come up with using this particular pair of distribution PQ will be a valid like trade-off function lower bound for M. In other words, M satisfies F differential privacy. So this has some really interesting consequences with what we've seen about the dominating pair. So effectively it says that for any mechanism, we can always find a particular pair of distributions that are not necessarily a particular pair of the distributions that are coming from a particular pair of data set that can be used to capture all of the differential privacy properties of this mechanism to completely characterize the privacy profile for this mechanism M. So two interesting consequences of this statement is that now we have a handle on something that we didn't get to prove about the advanced composition. So recall that for advanced composition, we've proven the version of the theorem for the case when delta is equal to 0. And we said that we'll leave the case when delta is larger than 0 when we have the tools available. Now the tools is available. So it turns out that there is a particular mechanism that achieves the privacy profile and the trade-off function point-wise for any epsilon delta dp mechanism. So this is called a leaky randomized response. So it is randomized response, but except that there is a small probability of delta that your distribution is just going to reveal who you are, right? So this is the case. So let's say that U is underlying data, and the PU outputs 0, 1 with this probability from the randomized response, but multiplying with 1 minus delta. But with this small probability delta, you just reveal who you are, say I am you. And similarly, like the distribution PV is defined by this discrete distribution with 4 possible outputs. So this is a discrete distribution, and this privacy loss random variable is easy to calculate. And condition on the fact that the event I am you or I am V is not happening, these random variables just becomes a standard randomized response. So what happens is that in order to analyze the epsilon delta dp for the general advanced composition theorem for any epsilon delta dp mechanism, it suffices to analyze the composition of this particular mechanism. Yeah, the second satisfying consequence is about the Gaussian mechanism. So remember that we said that the privacy profile is very useful for deriving the exact calibration of the noise for Gaussian mechanism to achieve any epsilon delta dp by just taking the difference of the CDFs of two of the standard normal random variable. But we also commented that it doesn't directly support composition. But what the theorem from the previous slide on dominating pair says that if we can show that this particular pair of Gaussian mechanism that is dominating, then by the composition theorem, the k-fold composition of Gaussian mechanism under composition will simply satisfy the property of differential privacy in the same way that a single Gaussian mechanism would have by adding up the privacy loss random variable. So notice that the privacy loss random variable for Gaussian mechanism are Gaussians, and since they are also independent, so we can just add them up, and the sum of independent Gaussians end up giving you a Gaussian distribution as well. To provide a bit more details on the advanced composition theorem, so let's take a look at the privacy loss random variable of the leaky leaky randomized response, and again, the privacy loss random variable is a function of a pair of data sets, or a pair of neighboring data sets, or a pair of distributions. So in this case, this random variable is equal to log of pu and over pv of y, and when y is drawn from p of u, and this becomes e to the power of epsilon when with probability 1 minus delta 1 plus e to the epsilon and e to the power of epsilon. Yeah, so this is epsilon. So how are we getting this? So this is a ratio of 1 minus delta e to the epsilon 1 plus e epsilon over 1 minus delta 1 over 1 plus e to the power of epsilon, and it is equal to minus epsilon with probability 1 minus delta 1 over 1 plus e to the power of epsilon, and it is unbounded with probability 1 minus with the probability the remaining 1 minus delta. It can also be seen that the inverse of this PV and PU behaves exactly the same way. Yeah, in other words, LPU PV is identically distributed to LPV PU. So with that said, that it remains for us to just to derive a tail bound for these particular sequence of privacy loss random variables, and the sum over L I from 1 to k PV PU PV so the probability of this is equal to positive infinity if any of this sequence of composition actually returns returns the pathological event that happens with probability delta, right? So the probability that this happens is the probability that this does not happen is 1 minus delta to the power of t, which is lower bounded with 1 minus k times delta. Okay, now it suffices to consider consider the probability and of this thing that is not equal to that is larger than say larger than t. So these are larger than t. Yeah, after conditioning on the sum PU PV is not positive infinity. So conditioning on these, like these random variables, simply becomes the pure DP random variables, and they're also like independent, and they add up nicely because yeah. So this remains a martingale. it remains a martingale with now that we're conditioned on this being not positive infinity, it means that this pathological event never really happens. So this is a martingale, and each individual random variables Li is bounded by epsilon. So the same technique that we used with a Zuma-Hofstadter inequality can be used to derive that this probability is smaller than this is smaller than e to the power of minus t kt square over epsilon over 2 epsilon square. And by working out the right choice of t to make this delta prime, and then we can recover the proof for the advanced composition theorem for the case when delta is larger than 0. Right? So what we got here is a very nice way of looking at the problem by reducing a more general theorem into a theorem where we into a theorem about just leaky randomized responses, and to show that the leaky, I guess it remains to show that the leaky random responses is indeed a dominating pair. And in order to show that, we can simply check that we can simply check that the leaky random responses, if we work out this trade-off function, it matches everywhere with the trade-off function that characterizes epsilon delta dp. Okay. The next thing is about composition of the analytical Gaussian mechanism, and it is like straightforward. Since the privacy loss random variable of Gaussian mechanism is Gaussian, so it is intuitively true. But in order to formally prove it, we need to use the machinery of the dominating pair. So let's say that N0 N0 sigma square over delta square and N let's say that N0 delta square and delta and delta sigma square is a dominating pair. And we've seen that if these are dominating pairs, then if these are dominating pairs, then then for the k-fold composition, then the N0 sigma square to the k and N delta sigma square to the k is a dominating pair for m to the k, right? So it remains to calculate the the privacy loss random variable for this, and because each mechanism is independent or it's a martingale in the adaptive composition case, then it can be easily worked out that easily worked out that the privacy loss random variable log of p q with p drawn from with the output drawn from p is just equal to the summation of this individual mechanism. That each coming from the privacy loss random variables of this PQ pair, right? And then clearly because the privacy loss random variable is the same and this is identically distributed to the privacy loss random variable of a single Gaussian mechanism. Yeah, it like this idea was proposed and applied more generally to beyond just Gaussian mechanism and epsilon delta DP mechanisms with a leaky randomized response. It was developed in the last couple of years. Something called the privacy loss distribution formalism that makes use of the distribution function of the privacy loss random variable, like and apply that to calculate the exactly tight composition of these mechanisms on the given pair of neighboring data set. And then they also come up with a numerical algorithm called a Fourier accountant to keep track of the Fourier representation of these privacy loss random variables probability density. And the idea is pretty neat. So basically you start with, so let's say that you have a privacy loss random variable X. Let's say that you also know the dominating pair. Suppose you are given this, and what you can do is to work out the density function of this LPQ. So let's say that the density function looks like that. And what the PLD formalism does is to first like making sure that this density is within a bounded support, right? By clipping the remainder of this density, by throwing away everything else, and then you can discretize this density into individual beings. And then this becomes a probability mass function with and this is an approximation that can be represented by a vector. So this will be a vector of P1, P2 to say P capital N, where N is a discretization factor, and let's call this parameter P. And then what they did is to apply the fast Fourier transform of P, which is a linear transformation of P that gives you the Fourier domain representation of this density function. Let's call this maybe P2. And once you are in the Fourier domain, you know that the addition of random variables is equivalent to the convolution. So suppose x drawn from P and x1 drawn from P and x2 drawn from P2, then x1 plus x2 is drawn from the convolution of P1 and P2's density function. But in the Fourier domain, the FFT of P1 convolution of P2 is simply so FFT transform something from the time domain to the frequency domain, and this should sound familiar to those who have electrical engineering background. But once you take the Fourier transform, whether it is fast Fourier transform, discrete Fourier transform, or continuous Fourier transform, and these properties are always true. Once you take the Fourier transform, and this becomes the pointwise product of the Fourier transform of these individual mechanisms. Yeah, so what the Fourier accountant does is that you can represent these privacy loss random variables discretized version of the density function in the Fourier domain, like using a vector of about the same length of the discretization, and then you simply do the pointwise multiplication of them together so that you can obtain the Fourier representation of the resulting composed mechanism, and then by simply running the inverse Fourier transform of this FFT P1 pointwise product with FFT of P2, and then we can use this to recover an approximation to the original problem of P1 convolution with P2. Right. So yeah, this is a very neat idea. And the key gist of doing this appropriately in the context of differential privacy, like it is clear, but the key challenge is that we need to bound the approximation error of this approach. We need to show how close this is to suppose you do not truncate and suppose you do not discretize. So there are discretization error and there are also truncation errors, and that's coming from this. By bounding all the errors together, you end up having like a useful numerical algorithm for keeping track of the privacy loss random variables. The next, I'd like to introduce the characteristic function representation of a particular dominating pair. So this is an alternative representation to the FFT representation that is in some sense more analytical and more precise. So the motivation is the following. And motivation is the following. So to recall that for every mechanism, like this inequality that holds for all neighboring data set D and D prime is a characterization of the epsilon delta dp. So from this expression, it's clear that all we need to know about these mechanisms, privacy guarantee is described by like two probability distributions. So one of them is this privacy loss random variable when the two distribution is P and Q, and the other is a privacy loss random variable when the distribution is Q and P. And using the fact that when we have a dominating pair PQ, and then it suffices to keep track of the distribution of the two two privacy loss random variables. One LPQ, the other LQP, right? And then we can hopefully use it to reconstruct by using this formula, to calculate the delta as a function of epsilon, or calculate the epsilon as a function of delta. And what we can do, because like representing the density function or CDF function of the privacy loss random variable is somewhat difficult to manipulate under composition. So what we're proposing is to represent their distribution function by its so-called characteristic function. So what is a characteristic function? So it's closely related to the Fourier transform, and it's also closely related to the moment generating function that we've seen earlier when we defined the Renyi differential privacy. So we call them phi functions of this M, and then for each M, there are two of them, one for LPQ and the other for LQP. So we're denoting this by phi and phi prime. And for each one of them, this is really the moment generating function, but with the order taken to be a complex value, taken to be an imaginary value. So when we have this imaginary value over here, and this is like essentially the same as a Fourier transform when the density function exists. And when the density function does not exist, the characteristic view is strictly more general. And the interesting thing is that there are many cases when the moment generating function of the random variable doesn't exist, or only exists with a very limited range of parameters of alpha. The characteristic function of any random variables, they always exist, and for all parameters of alpha. This is what makes it nicer numerically sometimes. And when we have this characteristic function for any random variable, and notice that in order to compute the epsilon delta dp parameters using the characteristic function, all we have to do is to work out the 1 minus the CDF of LPQ and the CDF of LPQP with a particular parameter epsilon. And the numerical efficient way of doing it is through simulating the Levy's theorem, which allows us to calculate the CDF of a particular random variable by doing an integral of its phi function. And this is not always analytically tractable. So what we propose to do is really to replace this with a numerical integral, and then because of this, this allows us to use off-the-shelf tools, say Gaussian quadratures, for numerical integration, and that turns out to be highly effective in practice, and it gives us the error bound like almost for free. So like why is it better to use characteristic function over the say the density function or the CDF function of the privacy loss random variables? I guess like if we so first of all, these are complex value functions, meaning that the output of these functions can be real or imaginary, or have a real component and imaginary component. So what we can do here is to show that if we just take the log of takes a complex log, it's a generalization of the standard logarithmic logarithm applied to the non-negative numbers. So the complex log can be applied to any complex number. And once we apply the complex log, then when we compose the multiple mechanisms having these dominating pairs represented in their phi function representation, and we argue that they compose it naturally, just like the Renyi differential privacy. Okay, so this is quite straightforward. So basically, if we take log of M1 of alpha and log of M2 of alpha, then we can recover the log of phi M1 M2 of alpha. And this like it's relatively easy to work out, and the argument is exactly the same, using the fact that this expectation is about product distributions, is about the independent distributions, and then since the moment generating function, the log of moment generating function would add up, and the complex version of the moment generating function should also just simply add up. And numerically, each complex log would return like two things. One is a magnitude, the other is a phase. So what this is saying is that the magnitude would add up and the phase would also simply add up. Yeah, it's a log of the magnitude would add up, and the log of the phase will become just angles, and the angles will add up, and then you take the modulus with respect to 2 pi, until since sometimes it goes over a circle. All right, so for many of the mechanisms that we are already familiar with, such as the randomized response, Laplace mechanism, and Gaussian mechanism, we know exactly what their dominating pair distributions are, and it's not very difficult to analyze. And the corresponding phi functions also are available in analytical form. So and besides these mechanisms, we also know the dominating pairs and sometimes tight dominating pairs for many other mechanisms. So this is kind of nice, because sometimes like all we know is that this mechanism satisfies pure DP, and sometimes all we know is that this mechanism satisfies approximate DP. But the fact that these pure DP mechanisms are dominated by randomized response, and the approximate DP mechanism are dominated by leaky randomized responses, and sometimes we can even work out the specific distributions that dominates all exponential mechanisms. And this makes it very flexible that we can mix and match and put a lot of these sequence of computations under the same formalism of dominating pairs. And the research goal on this thread of research in differential privacy is to continue to expand the list and work out more fine-grained characteristic function representations for each individual mechanisms. Yeah, so this will go on and on for the foreseeable future in phi functions. Yeah, I also wanted to point out that phi function is related to other mechanisms specific representation, to other function representation that we've seen like in the lecture, and they can be converted back and forth from each other. So specifically, just now we've seen that by the Levy's formula, we can convert the characteristic function to the hockey stick divergence or the epsilon delta dp, and by doing the Levy's formula and the integral, and sometimes doing Differential conjugate, and we can convert like almost every pair of these different representations back and forth from each other. Some of these conversions are numerically stable and some are not. And also I wanted to highlight that the reason why we have these conversions and they're all really mathematically equivalent is because we have a dominating pair and sometimes a tight dominating pair that's available, right? So that simplifies the discussion from having to work with an upper bound of all neighboring pair data sets to something that's more concrete and specific with just two concrete distributions in one dimension that we can write down analytically. And yeah, you may ask, like, where does the Renyi divergence, Renyi differential privacy appear on this picture? Yeah, so the Renyi differential privacy, as we've explained earlier, is a completely different object. So the dominating pair that dominates the hockey stick divergence might not be the same dominating pair that dominates the Renyi differential privacy. Yeah, at the moment, like, we are just focusing on the epsilon delta dp here and try to get the tightest possible privacy computation. Yeah, with all these said, and these dominating pairs and dominating pair of distributions and their corresponding privacy loss random variables and the phi functions, they can be used to create an analytical version of the Fourier content that we've talked about earlier. So instead of representing a discretized version of the probability density or probability mass function of the privacy loss random variable, now we can simply represent their phi functions in analytical forms. So these are symbolic functions that we can represent, and when we compose them, we simply add them, or we simply add the log of these phi functions up symbolically as well in both the magnitude, the log of the magnitude and the phase parameter of these imaginary valued functions. And what the analytical Fourier content can do is to, through the like conversion formulas that we've talked about earlier, it can be used to convert these phi functions into epsilon delta dp and support querying epsilon as a function of delta and querying delta as a function of epsilon, and also allows us to query the trade-off function that's implied by this dominating pair by outputting type 2 error, giving a type 1 error input. Okay, yeah, so I argue that this analytical Fourier content is kind of nice, and when we do have access to the analytic version of the phi function, this allows us to not making any approximations until the last step of getting actual numerical values, and for the error bounds in getting these numerical values, we can reduce the problem to standard numerical integral and make use of decades of research in numerical analysis to obtain like those error bounds. As a checkpoint, so far we've talked about the mechanism-specific analysis and the corresponding privacy accounting. Well, we've covered the pros and cons of various approaches of representing a mechanism by a function and converge to the analytical Fourier content, which represents the characteristic function of a dominating privacy loss random variable. We've seen that the ring EDP is qualitatively different, and we've also like even though it features a very natural composition, yeah, we've also seen that how we can make use of the phi function representation to get the best of both worlds in some sense. So when we have a dominating pair, then we can use the phi function to get a benefit of the natural composition of that just behaves like ring differential privacy. At the same time, this allows us to completely describe the corresponding privacy loss random variables, and so that the epsilon delta queries that we get in the end will be tight. Will be as tight as we have the privacy profile of the composed of the composition composition itself. All right. So we've finished all theoretical part of the lecture. So in the remainder of the lecture, I'm gonna give you a tour of the open source tool called autodp. So I'll also give you a demo of it. Yeah, so I won't have time to go into the introduction to DP machine learning with differential privacy, but this will be part of the next lecture. Yeah, so today we're going to be focusing on like practically implementing like these differentially private mechanisms and their privacy computation. Okay, so so these mechanism-specific analysis, they are nice. They are the main driving force behind a lot of the state-of-the-art research in differential privacy. On the other hand, they're somewhat complex and they require expert knowledge in order to derive these functions and manipulate these functions. Yeah, and any code written with this needs to be checked very carefully. And another limitation is that like we really have to derive, since this is mechanism specific, we need to derive like these mechanism specific representations for every mechanism separately. And that is a huge overhead. Luckily, as we've explained earlier, differential privacy is designed to be somewhat modular. So a lot of the more complex algorithms, such as the say private multiplicative weight algorithm, are actually created using simple building blocks. So there are various like algorithm design techniques that can be used to say like that can be used to extend the basic building blocks of these DP mechanisms, such as Gaussian mechanism and Laplace mechanism, into their more complex counterparts. Yeah, I haven't talked about these primitives such as amplification by sampling, amplification by shuffling, and post-processing, and so on. Yeah, but they loosely speaking, they are tools that allows us to make the privacy guarantee better with either pre-processing or post-processing of the output. Yeah, and the hope is that when we do mechanism-specific analysis, we'll also be able to convert a carefully designed and mechanism where we know a functional representation to the amplified version of the mechanism, and then to work out the corresponding functional representation for that modified and privately amplified algorithms after the pre or post processing. So it's somewhat tough to do, and many much of the research are available, but it is still hard to use by a layperson or by someone who just want to build differential privacy into their own application without necessarily wanting to understand like how to prove the privacy guarantees. After all, like it is impossible to get everybody who's interested in implementing differential privacy to take this particular take this particular course. Yeah, because it will be beyond the reach of most people, most practitioners. So autodp is a tool or open source package that aims at bridging the gap. So the layperson user can just describe how their randomized algorithms work. Say they can say that this is a composition of k Gaussian mechanism, and each one of them has the parameter sigma k1, sigma 1 to sigma k. Then what autodp can help this layperson user is to compute the overall privacy losses after the composition of or like other kind of combinations of their basic building blocks into this more complex algorithm. And autodp specializes in this, and it doesn't deal with the actual implementation of the mechanism, so it doesn't add noise whatsoever. But if you tell autodp that you are implementing, you implemented Laplace mechanism, and then autodp can help you to compute what is the privacy loss of that sequence of Laplace mechanism will give you towards the end of the day, right? So you can like install autodp very easily with a pip install command in your command line. So this is one snippet of the code of autodp. So what a typical user should do is really to somehow import from this largish library of different mechanisms that are already implemented, and then import like a callable object called a composition, and then declare these mechanisms. Say declare 2 Gaussian mechanisms and 1 sparse vector technique, and then you can compose this mechanism together into a new mechanism. Okay, so once you have done that, and then you can take the composed mechanism and then query for the epsilon parameters, like giving a particular choice of delta, and you can do it for any delta that you want. Yeah, what we can see is that this is the output supposed to run these get approximate dp with a delta parameter. It tells you that at delta equals to this, and the epsilon parameter is this. Yeah, so effectively this is giving you access to say evaluation oracles for the privacy profiles. And this is the inverse of the privacy profile, which just involves some kind of binary search of the privacy profile. Okay, you can also intuitively interpret the results that you got from this composition and this composed mechanism by plotting the implied trade-off function. Right, so the composition currently that's being implemented by the Renyi differential privacy. So this curve is what you would get for the Renyi differential privacy, and it involves like numerical optimization and multiple access to this Renyi DP functions of these individual mechanisms and their combination. But let's say that for the kind of trade-off function that you get over here, say for alpha equals to 100, then you get a trade-off function that looks like that, maybe. And when you get alpha equals to 5, then you get another trade-off function that may look like this. right? So at the end of the day, the kind of trade-off function that you get is a pointwise maximum for all possible alphas when alpha is larger than 0. So that's equivalent to taking some kind of a differential conjugate of the implied trade-off function that's given by the Rényi differential privacy. But all of that is out of the concern of the end user, and the end user only have to just create this mechanism like using this faction and based on the basic building blocks, and then like all these interpretable trade-off function representation, and maybe AUCs and the lower bound on the type 2 error when type 1 error is fixed at 0.05 and so on, they can be directly read off from this data structure called compose mechanism. So how does AutoDP work? It's an object-oriented framework that allows things to stay modular and easy to maintain. So there are three main classes of underlying AutoDP in its design. So there's this mechanism class, a mechanism class, a transformer class, and a calibrator class. And each one of them, you can implement, say, different mechanisms. Say a Gaussian mechanism inherits the base mechanism class. And transformers, it can be composition, amplification by sampling, conversion from add-remove version of the differential privacy into the replace one version of the differential privacy, and the conversion from the local differential privacy to curator differential privacy, and so on. And the calibrator is something else that takes a particular mechanism's definition and then try to calibrate the parameters of this mechanism according to the, say, the predefined epsilon delta dp bound, or to calibrate it according to a predefined Rényi differential privacy bound at a fixed given like alpha parameter. So this is nice because we will have a mechanism, and this mechanism can be somehow composed with other mechanism, like through the composition transformer, and it can be converted into another mechanism through, say, amplification by sampling. And the bad thing about it is that once you finish this transformation, you become the same mechanism class, and all the properties about that mechanism class, you can use it, and all the existing methods that had already been implemented are still going to be there. So there's this nice representation of a mechanism by their characteristic functions. Let me talk a little bit more of that. For the mechanism class in AutoDP, so this is AutoDP core, and mechanism. In the base class, it keeps various attributes that describe its privacy properties, such as the Rényi DP function, privacy profile, the FDP, and so on. So even though the FDP and privacy profiles, they are equivalent to each other, so when both implementations are available, it is a good idea to have both of them rather than relying on the conversion, like for numerical stability, and also for the preciseness of the evaluation of these quantities. Okay, it comes with a name and a dictionary of the native parameters. For instance, these native parameters would be, say, the noise multiplier sigma over the global sensitivity for Gaussian mechanism. So with these dictionary of parameters and the names, and it's easy for people to take this and implement the actual noise adding procedure in actual implementation of these mechanisms. Okay, so one interesting aspect of this mechanism class is that in order to declare a mechanism, all you have to have is just one of these descriptions. So they say, for instance, you know the Rényi DP function, and then you can simply use that to start a mechanism. And suppose you just know the Rényi differential privacy for some like fixed alpha, then you can use that to declare a mechanism as well. Suppose all you know about this mechanism is the satisfy epsilon delta dp for one particular pair of epsilon delta, then you can start a mechanism with just that, and all the other functions will be fulfilled, will be implemented using the conversions from this, like maybe very small piece of information that you provide about this algorithm. The transformer class, so I won't go into the details here, but it is anything that takes a mechanism and output another mechanism. It could be amplification or composition and so on. And as we use a transformer and it keeps track of the actual computational graph of individual mechanisms and how it actually works in practice. For instance, if we do a subsample Laplace mechanism, then the name will be automatically created by saying that this is Laplace composed with a subsample. And this symbol means that you first subsample your data set before you apply the Laplace mechanism to the randomly sampled subset. And on the other hand, for post-processing, the kind of transcript that will be created with a post-processing after after applying the Laplace mechanism. The last class of AutoDP is what we call a calibrator class. And the calibrator aims at finding parameter configurations of a mechanism such that a predefined privacy budget is obtained. So this is useful, as we've seen earlier, that we want the algorithm to be tweaked such that we can guarantee that for any possible input data set, you can get epsilon delta dp for epsilon equals to, say, 1.0 and delta equals to 10 to the power of -6. So how to do that in practice with respect to the native parameters of the mechanisms, say sigma for Gaussian mechanism, the sigma and the subsampling ratio for subsample Gaussian mechanism, and so on. So these are it's not clear like how to do that like very tightly. So sometimes we have a good tool that when we are given these parameters, then we can solve for the numerically solve for the epsilon parameter that you get in the end. But the inversion of that is often a lot more cumbersome. So the calibrator class comes to help with that problem. So it takes a definition of a mechanism which contains some kind of initialization tool or constructor that takes the dictionary of parameters and the given privacy budget, required privacy budget epsilon delta. Then what the calibrator does is to try to figure out what are the values of these parameters are in order for the mechanism to satisfy epsilon and epsilon delta dp. Yeah, so when there are multiple parameters to be tweaked, and often there are more than one possibilities to give you the epsilon delta dp, and some are better than others. So when we have a utility function that's made available in the data independent way, then we can do that type of maximization by finding among the configuration of the parameters that are that will give you epsilon delta dp, and you will pick the one that gives you the maximum utility. Okay, so underlying the AutoDP design, there are all these converters that are implemented, say converting RenyiDP to approximate DP, which effectively implements a lot of things from the conversion back and forth conversion table that I presented earlier in this lecture. So I won't go into it. And in addition to that, there are many templates. Say these are banks. Say the RenyiDP banks and the FDP bank, DP bank, and phi function banks, and so on. That implements these lambda functions, which takes particular parameters of these functions, and it gives you the output lambda function of say the RDP, FDP, or the DP for particular mechanisms. And using these basic building blocks, we've also created a large family of already implemented mechanisms in mechanism zoo, already implemented transformers and calibrators in calibrator zoo and transformer zoos. And these are just collections of mechanism definitions, transformer definitions, and calibrator definitions that people can just take and use. And because of these, like this open source project can easily accept like third-party contributions into it. And because many of these contributions will be directly going into these banks or the zoos that will have very little effect to the backbone of the backbone of the autodp pipeline. Okay, so for your project, you are encouraged to implement your mechanism, and if it is not already available, say in the mechanism zoo, you should consider contributing to autodp by implementing that in autodp and create an example or a tutorial of how that mechanism works. Okay, so for the remainder of the lecture, I think I just have a like maybe 10 minutes left. So I'll give you a demo of how to create a mechanism from scratch by looking at a Jupyter notebook. So this example that I'm gonna give is the example that we've learned in a previous lecture. I think this was from lecture 4 or lecture 5. So let's try to see how this mechanism on private multiplicative weight with sparse vector technique, and yeah, so remember that we talked about it with Laplace mechanism, but now that we've learned Gaussian mechanism, maybe we want to implement this mechanism with Gaussian mechanism to see what's the privacy utility trade-off. Okay, so recall that the algorithm is simply like trying to answer an online sequence of linear queries, or more generally, an arbitrary insensitive queries. And then we wanted to we wanted to figure out how to do it in a way that preserves differential privacy, and wanted to answer an exponentially large set of possible queries. Okay. I guess like this algorithm will try to create a synthetic data set, and if the answer is already accurate based on the synthetic data set, which we test over here, and using which we test using a private noisy version of do an approximate test by adding a Laplace noise here to the threshold. Yeah, if we passes this screening rule, it means that your synthetic data set is not very accurate, and in this case we use the Laplace mechanism to release the actual answer to that query on the actual data set, on the actual sensitive data set. So what I'm saying is that like we've analyzed this for Laplace mechanism, but now let's see how easily is it to use AutoDP to analyze a version of the private multiplicative weight algorithm we replace Laplace with Gaussian. Okay, so I'll move over to another shared screen where I can show you the Jupyter notebook. So just give me 1 second. Let me share the new screen. There we go. Yeah, I think this should work, right? Yeah. So can you guys all see the shared screen? Well, yeah. This is offline video recording. I forgot. Yeah, anyways, like this Jupyter notebook, which is something that I will share with you later, like describes how we can actually implement this online query release algorithm with private multiplicative weight using using autodp. So recall that autodp doesn't deal with the actual implementation. So this is how we use autodp to represent this private multiplicative weight mechanism and actually calibrate its many parameters so that we can say use it to achieve a predefined epsilon delta parameter. Okay, so first of all, like we've seen from the slide that this algorithm is trying to learn a synthetic data set, a histogram of such data set in a discretely supported data space, using online learning, using the multiplicative weight algorithm while like keeping it differentially private. Yeah, from the AutoDP point of view, like the private multiplicative weight algorithm is like nothing but a composition of k mechanism for checking the threshold, for screening the input queries. We call it the above threshold algorithm or the sparse vector technique. And it's a composition with the also k Laplace mechanisms, or in our case, the Gaussian mechanisms that are interlaced in between, right? Since it's a composition of all these mechanisms, and the online learning guarantee tells us that in order to achieve the alpha accuracy, then the maximum number of times that we have to run this is this much, is a log cardinality of the data space over our alpha square. And a log cardinality of the data space is often just proportional to the dimensionality of the data. Okay, so having say a linear dependence on the dimensionality is reasonable. Okay, so we'll replace Laplace mechanism with Gaussian mechanism, and we will also like choose the parameters of the mechanism numerically rather than according to the theory, which have a bunch of numerical constants that we sometimes do not know how to set in practice. Okay, so the AutoDP can be used to help with that. Well, so first of all, like with this realization that this is a simple composition of k Gaussian mechanism and k above threshold or sparse vector technique, the implementation of this in AutoDP is quite straightforward. So we basically import Gaussian mechanism and the pure DP mechanism from the mechanism zoo. So, and notice that the sparse vector technique or above threshold is a pure DP mechanism described by its parameter epsilon. And the Gaussian mechanism, let's say that it is described by its noise multiplier sigma that is defined to be the actual noise, the actual sigma that you use over the L2 global sensitivity. Okay, then I also import the composition from the transformer zoo and then instantiate this composition with a callable object compose, right? And then the next line, I'm going to compose these two mechanisms each for k times, and this completely describes the private multiplicative weight algorithm when their parameters is set to be like these three numbers. Okay, so notice that there's also a hidden parameter that is what the threshold is to be, but yeah, that is of no concern to the DP algorithm. So even if this threshold is chosen to be arbitrarily haywired and not according to the theory, and it's not really going to affect the privacy guarantee of this mechanism. Okay, so let's run that. And as we can see that once we run this compose mechanism and then use this get epsilon or get approximate DP with a given delta, it outputs this epsilon parameter by doing all the mathematical analysis underneath. Okay, so it's quite easy to create this mechanism object on the fly if you know what these parameters what is this parameter to choose. But often, like in practice, what we want to do is the opposite. So we want to go from, say, this epsilon being, say, rather than 7.7, let's say we want to calibrate it to 0.2 or 2 or 0.5. then with delta equals to 10 to the power minus 6, then the question is that what is the corresponding sigma epsilon k parameters that can give us those parameters? And also AutoDP can help with that problem as well. So here's a standard way of doing it. So what we should do is to put this like implementation of the mechanism and wrap it around a function. Let's say that create complex mechanism. So this is doing exactly what we explained it does to describe the private multiplicative weight algorithm with these given parameters chosen. And then this will return the composed mechanism, which has everything. And what we're gonna do is to create a mechanism definition out of this. So it is also straightforward and somewhat standard. So we import this mechanism class. We inherit this mechanism class and create a new mechanism class, right? And then all we have to do is to define a constructor of this new mechanism class by calling this create mechanism. So what this does is that you take the parameters, you parse these parameters into and save them as part of the parameter object, parameter dictionary in this mechanism, and then you call this create complex mechanism to create this new mechanism. And once you finish that, what you basically do is to say that let's set the all the representations of the current mechanism private multiplicative weight mechanism definition using this mechanism object that's created on the fly, right? And then this becomes a legitimate mechanism class definition, and later we can instantiate it using the calibrator to choose the parameters accordingly. So while it is possible to simultaneously optimize over sigma, epsilon, and k, and there are going to be like I explained earlier, multiple configurations where we can get the epsilon delta dp. And at the moment, we're not yet like gonna tell you how to maximize a utility function, and we also do not have a utility function. But what we want to do is to go from like a slightly theoretical route by figuring out the ballpark of what these parameters are and how they depend on the target alpha parameter, right? So one of the key challenges of applying this sparse vector technique and the private multiplicative weight updates is that we don't really know what is the right choice of alpha given these other parameters of interest, right? So we could choose it by theory, but then it is likely to be more conservative than needed. So what we're gonna do is to set this gamma as a variable, and then couple this gamma with all the other three parameters, sigma, epsilon, and k, and then try to figure out what is the smallest gamma that we can get so as to achieve the predefined privacy budget. And then the AutoDP will automatically instantiate what these parameters this epsilon k is for us, and using the same formula we can figure out like reversely what's this gamma that is used to give us epsilon delta dp. Okay, so to instantiate these equations, let's set this n to be 10,000. So this is the size of the data set. I'm just cooking this up, and you should obviously plug in the size of the actual data set here. And this C parameter is some numerical constant that captures the logarithmic factors and the constant factors from the analysis. So those could be really untight, but let's say that we'll just not worry about that and set this to be a practical number 10, right? And lastly, like the log of X cardinality, this is something that suppose you know what the data space is, so you know exactly what it is. In this case, let's say that we have a 20-dimensional binary feature vector. So we'll set this to be 20, right? And since C is fixed and log X is fixed and N is fixed, and this becomes like a one-dimensional optimization problem. We just want to find a feasible solution alpha such that like these parameters gives us epsilon delta dp. And what we can do is to further inherit this private multiplicative weight mechanism and then create a new constructor that takes only this alpha as an input parameter. And then we can just implement these formulas by passing this into the constructor of the private multiplicative weight mechanism definition that we defined earlier in the previous class, right? So after putting this in, then we're ready to calibrate the parameters to the mechanism. So let's make sure we run this. Let's make sure we run this. Okay, it finished running, and it remains to just calibrate all the three parameters by choosing appropriate alpha. So this can be thought of as finding the best possible like error that you can get given the constraints that you have, that is epsilon and delta. All right, so what we do is to just import this standard epsilon delta calibrator from the calibrator view, which is something that's already implemented that allows you to call it to do the numerical computation by finding what the right choices of this alpha should be. So you pass this mechanism class, private multiplicative weight mechanism described by a single parameter delta alpha, and then you choose your desired privacy budget, say in this case 2.5 for epsilon and 10 to the minus 6 for delta. And then that's basically it. And then you can run this and then just read off what the right choices of these parameters by just looking at the parameter dictionary that's already encoded in this mechanism object, right? And then we can reconstruct this alpha using any one of these three formulas. Okay, let's run that. Yeah, so we can see that what this is telling us is that like we should just set k to be this number, right? We can round it up to or round it down to the nearest integer, like the noise multiplier for the Gaussian mechanism that we should use is about 110, right? So the actual noise you add is 110 multiplied with a L2 sensitivity. So in this case, it's 1/n. So you multiply this with 1/n. And for the epsilon parameter that we use to instantiate the above threshold or sparse vector technique, the choice of it should be about 0.001. Right, so the actual noise, actual epsilon that you choose is gonna be this and multiply with the sensitivity. Now with the actual noise that you add, it's gonna be this divided by the sensitivity. Okay, so and then the corresponding of choice of alpha can also be computed here, and we can use this alpha to choose the right threshold of the private of the multiplicative weight mechanisms, like by choosing the threshold proportional to alpha. So the theoretical choice would be the fraction of alpha, but we could do it with, say, we can alternatively do it with just a quarter of alpha or half alpha without worrying about those numerical constants. Okay, and what this is saying is that notice that we're calling this get epsilon. What the output says is that it's exactly what we wanted to achieve, right? So we get the epsilon computation in the end, which says that this, when you choose these parameters appropriately, then this mechanism is certifiably 2.499997 and delta differentially private. Okay, I hope that like this demo gives you a flavor of how autodp works and how you can make use of it to help with your numerical experiments and actual deployment of differential privacy tools. All right. with that, I'm gonna end the lecture. So in the next lecture, we're gonna be talking about the new chapter on differentially private machine learning, and that's what we're gonna do in the next lecture. Yeah. Yeah. Sorry for the glitch and the technical issue that we run into today, but hopefully my recording like gives you enough details for you to get started with AutoDP and understand the mechanism specific analysis. I'll see you guys next Monday.